Hi, operating systems class. I wasn't entirely happy with my explanation of using fork and exec in class. So this afternoon I put together an additional example that I think will be helpful as you work on your shells. So let's give it a look. So the goal of this program is to do the equivalent of running ls-l grep cargo piped into wc, which is the word counting program. So let me go ahead and execute this in a regular shell so you can see how it works. So if I run this, it says that ls-l grep cargo outputted 2 lines which contained 18 words and 118 characters. So we're going to set up this execution in this example program here. We're going to take it from top to bottom. So at the top, we have extern crate nix. So this is saying this is an external module. Crate is the Rust term for a module. So there's an external crate we want to use. You need to add this text right here, nix equals 0.7.0, to your cargo TOML file. Let me open up mine and I'll show you what it looks like. So here's my TOML, and I added nix equals 0.7.0. And that goes to crates.io, which is a server that the Rust people run, and it's a master directory of crates. So anybody can create a crate, register it there, and then cargo goes there and figures out where it's stored, usually on GitHub, and then it'll just install it on your machine when you're ready to compile. So from here, let's see how this is set up. Lines 11 through 15 are about setting up the C string object so that we can pass values to exec. So I just created these as vex, and the reason that I did it that way was when you do your own string processing, I'm sure the result is going to be a vec of strings in some form. And so I want to illustrate how we're going to convert that to a fixed size array. So I create my vex in place in this case, though. And so this is how we take a Rust string and turn it into a C string. If you weren't using a literal, then you would need to make sure you converted it to bytes. So do it a .as bytes. When you pass it to cstring.new. And .unwrap is okay here because it's only going to be an error if there's something malformed about the string, a null character somewhere in the middle of it. I want you to note that when I set up these arguments, the program that I am executing, that name is always the first argument. If you don't have that in your arguments list, there'll be problems when you try to run it. Okay. So we've got that set up. We're ready to fork. Just glancing ahead, I have 3 calls to fork. So there are actually going to be 4 different processes. What are the 4 processes? There's this process, which is like the master process, just setting everything up. And I preserve that as its own thing. Your shell will be doing something similar, so if your shell is executing a pipeline with 3 commands, you're going to have 4 processes running, one of which is your shell, and the other 3 of which are those commands. Okay, so let's dive into the first fork. So here I use fork.unwrap. Now I don't want you using unwrap here. If fork has an error, you should be handling the error. It's really not okay for a shell to panic, even if fork is causing problems. So assuming you've handled that error somehow, we then go into the match. So a fork result either gives us a parent with the PID of the child, or it gives us a child. Let's go ahead and put a blank line there. And so just to illustrate that the child is really just an int, it prints out the PID of the child, and that child is going to be the WC process. Now remember, when we're executing a pipeline, the highest level child of the parent is actually going to be the last one in the pipeline. And the reason for that is once this command exits is when the shell resumes control. The shell is waiting on this guy, who in turn is implicitly waiting on this guy, who in turn is waiting on this guy. And what do I mean by waiting? I mean waiting. So wait PID is a system call where you give it the process ID of a process that you want to wait on. And then there are some various command line options, none of which I cared about here. So I just used option none. And so this causes the process to block until the child has finished executing. Now note that if you were putting this in the background, which is also part of the assignment, you wouldn't wait. You would just let it execute. But in this assignment, that's not always the case. It's only if it's in the background that you wouldn't wait. Otherwise, you're going to wait. And wait PID is the way that you do that. Again, make sure you do error handling. And then once it's done waiting, it will print this finished message here. And part of the idea is that we can watch these print statements to get a feel for what the actual execution ordering is of this program. So that's what happens when we fork and we're in the parent. Well, what if we're in the child? If we're in the child, we need to set up WC. And the first thing we need to do that is to create a pipe. So this is calling the Unix pipe system call. The first return value in the tuple that you get back from it is going to be the output of the pipe. That is the part of the pipe that you can read. A pipe is one way. Then the second file descriptor it returns is the input to the pipe. It's the part of the pipe that you can write to. And I went ahead and labeled these variables with the names of the commands that we're going to be accessing them in that way to make the code easier to follow. So I'm in my child. This is the WC. I've created my pipe. And now the next thing I do is I fork again. Well, the reason I need to fork again is that grep is going to be a child process of word count, WC. So I fork. And now if I'm in the parent, I am now in the WC parent. Now here's where things get a little bit intricate. This system call dup2 is extremely important. What we do with dup2 is this second argument is a file descriptor that corresponds to standard input. So file descriptor 0 is always standard input. But that's not what we want. We want input from the pipe. So what dup2 does is it basically says this second argument, close that one and replace it with this one. And so that lets us spoof standard in to be the pipe. So whatever's coming out of the pipe comes into my WC process, and standard in no longer does. Now this next line is very, very tricky and subtle. So let's come back up here and think about what's going on. I created a pipe and then I forked. Well, at that point, both the parent and the child process have their own copies of these file descriptors. And if any process maintains copies of those file descriptors, the pipe stays open. If the pipe stays open, well, your program's going to hang. It's not a lot of fun. So the part of the pipe you're not using, you need to explicitly close in your process. And so that's what we do over here. So I'm in the parent. This is going to be running WC. And so I'm going to close grep out because I'm not going to write anything to the pipe. There's no need for me to do that. So I close it. And it's very important that I close it here, because if I don't close it here, it's never, ever going to get closed, which would be a tragedy. So I close it, and now I'm ready to execute. To execute, I have to take my vec, so my vec back up here, and I need to convert it into a boxed array. And so that's what this command does here, the into boxed slice. So that gives me an array view of my vec. Now I call exec VP. So what am I doing here? Well, array 0, you remember we put our command as the 0 element of the array. So now we take advantage of that. So the name of the program we're looking for to be searched for in the path environment variable. is an array 0, and I am passing this by reference because that's what execvp is looking for. Over here, it's a little tricky, so let's break it apart. Star array means because this array is in a box, the star says do a dereference. In other words, array is really just a pointer to an array. The dereference says, okay, give me the array. But then execvp wants me to pass it by reference, and so I have to have my ampersand there. And that's it. So execvp will then overwrite this process and begin executing a WC that has as its input that WC in part of this pipe. So let's look at the other half, right? So now we're in the child. So in the child, just as up here, we didn't really care about grep out anymore. Down here, we don't care about WC in anymore, you know. So in each branch of the fork, there's one end of the pipe that we explicitly need to close. Might make it even clearer if we move this line up here. That'll just make it a little more symmetric. But now in this child, this child process is going to be grep. And so it needs a pipe that's going to connect it to LS. And so what I do is I call pipe again. So I call the pipe system call, and I get LS out and grep in. Notice that this pipe up here has the output of grep. This pipe down here has the input of grep. So now we fork again, and in this final fork, when I'm in the parent, I'm going to use dupe2 on both the input and the output. So I'm going to just move this close up here. There we go. And yeah, just keep the code kind of symmetric all over. So I first have to get rid of standard output. So standard output is always file descriptor 1. So this dupe2 closes standard output, so my text will no longer go to the monitor. And it says instead, let's have grep out, the output of this pipe over here, be my output. It's technically the input to the pipe, but the output from my process will be that pipe. And then I get rid of standard input, and I replace it with grep in, which is the readable part of this pipe over here. And now that I have the input and the output set up, I'm ready to execute grep, and I do it the same way that I executed WC. I take my vec, make it boxed, and do the execvp. It's really just the same thing. Then finally, in the child, now we're done forking. The child is where we're going to run ls. So in this case, what we do is we redirect the output. So we close standard out. We replace it with the reference to the writable part of the pipe. So ls will be writing to the pipe instead of to standard output. We then close our copy of grep in to make sure it goes away. We then execute it. And there it is. So let's run this. So cargo run. And sure enough, look here, here's where I called lsl grep cargo wc. Down here is the exact same output I got up here. So I did the same thing. Let's go ahead and see what else the program printed. It said that the WC PID was 15379. And isn't this funny? They're consecutive. grep PID is 15380, ls PID is 15381. And then when we're done, we print the finished message. So let's jump back to the program and just see where those messages get printed. So coming back here, we first saw WC, then grep, then ls, and then the finished message. In the code, the very first print is the WC, and then we wait on that child to finish. Well, before that child finishes, we also see printed the grep PID and the ls PID. And only then do we then see our finished message. But before we see the finished message, of course, we see the actual output of the pipeline, which is right here. So putting that all together gets us a nice model of how we can do pipelining in Rust using this Nix crate, which makes it safe to, which gives us these safe wrappers to these Unix system calls. So have fun with that. Remember, this approach is optional for this assignment, but I think overall you're going to find it pretty satisfactory if you choose to undertake it. This is obviously the skeleton of what you'd be doing, but you're going to need to think carefully about making this work. Certainly when I test your shells, I'll be testing them with pipelines that have a lot more than 3 programs in them. And so you're going to want to make sure that you can handle some really nice long pipes, and so you write your code accordingly. You can't write it assuming ahead of time that you know how many pipes you're going to have. Personally, I thought this was easiest to implement by using recursion very carefully. Your mileage may vary. We shall see. Good luck on the assignment, and I hope this was helpful.